Hello, my name is Phil Varden and I'm an Associate Professor at Delft University of Technology. In this video, I'll talk about different thermal energy sources and their characteristics which are important in order to enable integrating them into an intelligent energy system. The learning objectives of this video are to be able to identify different thermal energy sources, in particular for use in sustainable thermal energy systems, and to be able to describe their key characteristics. The characteristics that I describe are those that are typically important for integration into the wider energy system. The key characteristics include the following: the scale of energy supply, i.e. the amount of energy which can be delivered per system, or the number of buildings which can be supplied. These are characterized as large, where many users have their demands satisfied and large-scale heat distribution is required, and small, which are more local and only limited distribution is required. The heat quality, or temperature, is another key characteristic. So high quality, or high temperature, heat is much more energy dense and is much more flexible. It can be transported over longer distances and used for more purposes. Low quality heat is, however, more easily available and can be cheaper to obtain. The ability of the source to provide only heating, or both heating and cooling, is a key characteristic. Often the lower temperature sources can offer both heating and cooling. However, these often also require a heat pump and electricity to run the heat pump to do so. The final characteristic is how available thermal energy supply is over the year. Some thermal energy sources can constantly supply energy. This is known as a baseload supply. Other thermal energy sources can supply different amounts of energy throughout the year. Often these are influenced by the outside temperature, and these are known as being seasonally variable. We'll now move on to looking at several different thermal energy sources. Geothermal energy is the extraction of heat from the ground. In a typical project, 2 different wells are drilled several hundred or thousands of meters into the ground. Hot water is pumped to the surface, the heat is extracted, and the cooled water is then returned to the ground. The energy supply is large scale, it's a base load, for heating only, and it's high temperature, normally over 70 degrees Celsius, but it can also be cooler or sometimes much hotter also. And when it's much hotter, it can also be used for electricity generation. To install a geothermal system, deep drilling is needed, which can be costly, and how high flow rates are required in the subsurface. The depth required to be drilled is dependent on the subsurface properties in the local area, as is the temperature that's available and the flow rate that can be achieved. These aspects make the problem challenging, but can supply a substantial amount of energy in one project. Another source of thermal energy, which is becoming commonly available, is waste heat from data centers. These data centers drive the internet and are used by many companies for data analysis and computer simulations, among other things. When the data centers are running, they become hot and require cooling. The heat extracted can then be used elsewhere for heating purposes. Data centers offer the possibility to supply several buildings, so they can be considered a medium-scale source. They supply a base load as cooling is required year-round, can only provide heating and not cooling, are of a moderate temperature, so around 40 degrees Celsius. Due to the moderate temperature, the heat user needs to be relatively close to the supply. Shallow geothermal energy works by circulating a fluid through closed pipes installed into the shallow subsurface, and that's usually around 100 meters deep. The temperature at this depth is strongly linked to the average annual temperature and is then between about 12 and 15 degrees in the Netherlands. Shallow geothermal energy is a small-scale system which can vary its response to demand. It takes advantage of the relatively stable temperature at a few meters below the surface, and the system can provide heating and cooling from the shallow subsurface, which is at a low temperature. Due to this low temperature, the source needs to be close to the demand and requires the use of a heat pump for heating and often also for cooling. Air source heat pumps have similar characteristics to shallow geothermal energy. They're small-scale, variable systems which can be used for heating and cooling and operate at a low temperature. They also work in a similar way to shallow geothermal systems. They use a fan to move air through a heat exchanger to change the temperature of a fluid. This fluid is then pumped to a heat pump where the temperature is upgraded to the required temperature. However, when we want heating, the air temperature is usually cold, and also the opposite way around. This makes the system less efficient than shallow geothermal. However, it is much cheaper and easier to install. It requires the use of a heat pump for both heating and cooling. Solar collectors are usually mounted on the roofs of buildings. They turn the radiation from the sun into usable thermal energy. They can be combined also with electricity production, with panels which are combined with photovoltaics. This actually makes the electricity production also more effective by cooling the panels. Most heat is of course available when the sun is directly shining, which happens most commonly in the summer. So solar connectors can be characterized as small-scale variable heat supply systems, and they only supply heat. They can operate at a variety of temperatures, but they're mostly warmer than shallow geothermal and air source heat systems, but cooler than geothermal energy. Aquathermal energy uses surface water to extract the heat. It's relatively similar in characteristics to both shallow geothermal systems and air source systems, although can be more easily used at larger scale. Surface water needs to be available, therefore a lake, a river, canal, or some other watercourse is needed. As the temperature is low, the user also needs to be close to the source, and a heat pump is required. The temperature is usually between that of the deeper subsurface and the air temperature. So, to recap, we have geothermal energy, where large amounts of heat is extracted from the deep subsurface, data centers, where medium amounts of heat are obtained due to cooling in data centers. Shallow geothermal technology extracts or injects heat in quantities suitable for individual buildings from the shallow subsurface. Air source heat pump systems, where the heat is exchanged with the air for use in individual buildings. Solar collectors turn radiation from the sun into usable heat, and aquathermal energy collects or injects heat from surface water. Geothermal energy is a large-scale source, and data centers and aquathermal energy sources are medium-scale, whereas the rest can be considered small-scale domestic sources. The highest temperature source is geothermal energy, which data centers and solar collectors provide medium temperature heat. The other sources are low temperature sources, which require heat pumps to operate. Geothermal energy, data centers and solar collectors provide thermal energy for heating, whereas the other systems can provide heating and cooling. Geothermal energy and data centers provide baseload heating, where all of the other sources are variable throughout the year. This concludes the lecture. Thank you for listening.